And William, if you can flip it on your end too, that'd be great. Okay, so the next thing that we're going to do is we're going to start talking about this tutorial on multi-charts. And before I do that, I kind of want to point out that on this particular tutorial page, and I'm going to share a screen on it, you'll notice that inside of this, there's this kind of complicated chart. And I'm not going to go through every little detail of this chart. I just kind of want to give you a high-level overview and tell you that it exists, basically. And that is, different kinds of charts have different types of options that are available to them. And you can imagine why, right? Like you might have bars or no bars, or lines or no lines, or splits or no splits and stuff like that. So like, for example, a histogram isn't going to have a donut hole percent. So if you're interested in which charts support which functions, you can look at this chart and it will give you a list of them. I mean, a table of them across the board. And similarly, there are functions related to various other kinds of chart stuff, like the bin width and the line density and the point density and stuff like that that we can adjust. And we'll play with a few of these today. Now, I'll remind you that it's not always the case that these have a pure accessibility overlay, but they don't need to necessarily. For example, if I make the point density higher, does it really matter for a screen reader user? As long as they can access the information, it might be useful to say the size of the point, but it's not clear that it matters unless it's that kind of a chart, like it's a chart that's supposed to explore density in some way. My point is, sometimes there are purely visual things that don't have an accessibility piece, but that's only if we've provided the information to the screen reader in a different way, right? We'll get to some examples of this kind of stuff in a bit. Okay, so now that we've mentioned that, what I want to spend a little bit of time doing in this one is let's first just do a little bit of playing, but not much, just with one of these functions, just so you can see what it looks like. And that is, let's try this set point density function. And so I'm going to put that into the chat. It's in there. And I'm going to put it in mine, and then I'm going to show the chart just so you can see what it looks like. And in this particular case, you'll notice that if I set the point density higher, what I do is I get big points. I'm sure this is very shocking. I'm sure you're all shocked. When you tell the points to be larger in size, they get larger in size. Ta-da! Hooray! Yay! We're done. No, I'm just pointing out that you can make some visual adjustments like this. That's all. And there's a number of functions that are in there, so you can do stuff like this. I think we can do the line density too, although I'm not positive it goes for the regression line, but let's try that too. Oops, there we go. So let's also try the line density. Set line, oops. And it's possible Hannah will kill me if this only applies to the lines, not to the...
It does. You have to put set regression line density.
Sorry, what?
You have to put set regression line density.
Oh, thank you. Oh, I didn't actually realize that. Okay, see, this is the benefit of having people here that actually know what they're doing. Okay, now I'm going to stop it and I'm going to run it.
Oh, you can also set the color of the regression line.
Yep. So in this case, it's the same, but you can change it. And visually, what we observe is that the line is thicker, right? And that, cool. I'm not necessarily saying that, you need to do any of this kind of stuff. I'm just pointing out that you can, right? That's really it. You can adjust the visuals if you want to. It doesn't really change the accessibility a whole lot, if anything, but if you want to change the purely visual aspect of it, you can still do that. Okay, but let's get to the meat. If we go back to our data set, our insurance, we notice that some of these attributes seem to be different than the others, right? Like when I look at charges, this looks like it's pretty much a quantitative variable. Charges is probably money charged by the insurance company or something, but I don't know exactly. And it's just numbers between, I'm not sure, maybe 0 and, since it's insurance, 1 million, 1 billion, I don't know. Some arbitrary number. But then you've got other variables like region. These aren't really quantitative. They're more categories of things. Right? Southwest, Southeast. And when we showed these earlier, there was one person, I think it was Tiffany, she had a hypothesis that the Southeast, I'm sorry, it was Louisa, that the people in the Southeast region seem to have a higher BMI, which I sort of thought might be true as well. And I think Derek mentioned as well. So one of the things that we can do inside of coding is we can add these not as a column, but as a factor. So what I want to do, oops, wait, where do we go? Let's go BMI. Let's go BMI in children again. Instead of age child's, which is amazing, but perhaps not the most meaningful thing in the world. And what we're going to do is, instead of saying add selected columns, we're going to say frame, add selected factors. And we're going to put in one of these categorical variables, specifically region, that has multiple pieces in it. And so to say what this has, I'm going to put it in Slack. We've got a column children, we've got a column BMI, and we've got a factor region. We'll talk about what that is in a second, but let's run it first and just see what it does. No, I guess I didn't change that. That's okay. All right, now I've got a rather complicated graph. In this graph, I've now got 4 colors. They're all mixed together. Right? This isn't actually a very good chart, but bear with me for now. I've got 4 separate things that I'm wanting to take care of. I want to look at the relationship between children BMI, but only for the Northeast, only for the Northwest, only for the Southeast, and only for the Southeast. In other words, the question that I'm asking here, hypothesizing about, is, does it look like the relationship is different for each of these regions individually? Do we get a different equation that pops out when we calculate this for each region? But there's a problem with this chart. What is the problem with this chart? Visually, is it very easy to read?
No.
No, not so much. And even from a screen reader perspective, I forget actually what the traversal order does in this case, but I recall it's not easy either, right?
You go down by each of those little points down the column.
Yeah. And when it does, it tell you the factor for each one? Is that what it does?
I don't know.
Yeah, it's pretty hard though, isn't it? I
Yeah.
would say. So, and visually, it's not easy either. So what we're going to do is we're going to learn in this particular tutorial a lesson about what in some communities, they have different names in different communities. In the R community, they call it facet grids. And in Quorum land, we actually haven't done a study yet on what it should be called, but for now, we're calling it multi-charts. It's maybe not a great name, but let's give it a shot. So we're going to go back to our code. And we're going to keep this the same. We're curious about the same question. But what we're going to do is we're going to add, I'm going to change that point density down to something that's not insane. 5, and then maybe I'll keep that at the same. I'm going to say chart, and then I'm going to say separate. And you'll notice when I say sep in code completion, you can verify this in a screen reader too. There's separate by factor Boolean, separate by factor integer request columns, separate by series Boolean flag, and separate by series integer requested columns. Now, you're not going to know what all these are, and it's going to be easier to just kind of show you what they do. Okay. So notably, I'm going to start out as I'm just going to say separate by factor. Okay, and then I'm going to run my code. And I'm going to share screen to show the chart. Okay, now what this chart did, instead of now showing me all the points put together, it now has 4 separate subcharts, and these on a screen reader are also separated, so you can traverse them with the arrow keys to get to them. And you can then see the trend line for each one individually, and you can see the points individually. If I want to traverse this with a screen reader, and I'm on my Mac, so since I'm doing this on desktop, it's not going to help you very much. I still press tab to get to the pieces, and then I press enter, and then I can use the arrow keys to go through them, and then I press enter on each chart individually.
Okay, yeah.
So the idea is that now that we've got a multi-chart, you can orally or visually separate out the data so that you can examine individual pieces. But let's go back to our spreadsheet for a second. This is important to remember why. The reason we care about this is because there's 2 ways we could make this chart. One is we could go in, find every single row that had a different value, separate them all manually, and then we can have it make the chart for just that chunk. Or we say separate by factor, we add it by a factor, and blammo, we've got an automated system for separating all this out. With me so far? Okay. Let's do a couple more little mini functions inside of here just to make sure you understand. And then let's get to the data science for like why you would bother to do this. Like, what are you trying to do when you're doing operations like this? What is your goal? So when we say separate by factor, another thing that we can do here is we can pass a Boolean flag, or we can add the number of columns. I'm going to say separate by factor, but instead of passing nothing, I'm going to pass 2, which means make a 2x2 grid of charts. So if I run this one, now instead of a 1x4 grid, I've got a 2x2 grid. And the reason you might do this is because if you're publishing a paper, an academic paper, you're putting something online on your website, sometimes it just looks nicer, right? And so even though from an accessibility perspective, it really doesn't make any difference at all, we have to remember that one of the reasons why we built this to be both visual and accessible is because we're always worried when we build accessibility technologies that if we make it only for people with disabilities, it won't get adopted. If instead we make the technology universally designed so that you can use it for any purpose and it's also accessible, it has a better chance of adoption broadly. And more crucially, it's just more useful for everybody because anybody can use it. I can use it. You can use it. Your friend can use it. It can give explanations. It can do all sorts of stuff. So the point is, you have some customization options for these graphics for figuring this stuff out. When you navigate it, it's the same way. So I press tab, press enter. I can then traverse through the charts. I can press enter into them. And it does get a little bit tricky to go point by point. I think that's probably something that will be changed on the accessibility side, because it's just too much when you've got large data sets. But we've tried a few experiments on what it should be, and none of them have been conclusive so far in terms of how you should traverse or navigate these particular scatter plots. Now we have ideas, but when you've got 1 million points, well, what if you want the points? You know what I mean? So like there's no magic here. So okay, so that is separating by factors. Separating by factors. Before I move to the next topic, any questions, comments, concerns? You kind of get why you would do that? Makes it a lot easier to read. Okay. All right. So the next question then is, why do we do that sort of thing? So usually when we're talking, if we go back to the data set, if we're talking about data science, one of the reasons why we care about things like separate by factors or facet gridding is because we're using it as an exploratory system. So what I would like you to do next, and I'll give you a few minutes to do it, is assume that the two selected columns are children and BMI. And then I'd like you to make a facet separation or a separate by factors for other variables you think might be related. So have the factor be age, have the factor be region, have the factor be sex. And then you tell me what you think the relationships are between these things. So for example, does sex seem to matter when you look at these charts and you interact with them? Does the region matter? Does it seem like that makes a difference? So the question scientifically that you're asking here is, if I have a relationship between children and BMI, are there other factors that get in the way? Does the region impact your interpretation? Does the age impact your interpretation? All those things can matter when you're looking at data analysis and you're trying to rule them out. Okay, so we're going to take 5 minutes. I'm going to let you go through and just all you have to do is change the one line of code, the add selected factors, change it to the other factors that you think might be interesting from your hypothesis. And then we're going to have a brief discussion about which ones whether they probably matter in the context of this data set. So again, this is the kind of thing that you might want to do with students. They're exploratory tasks, right? To try to figure out a data set, not just make a chart. Making a chart is kind of by rote. But what you really want is for kids to explore the data and come up with their own ideas. Okay, so 5 minutes at the most, and I'm going to do this myself as well. Five minutes. 10:23. When you're done, you can put the call out in as well.
Mine keeps not responding.
Sometimes these do take a little bit to render. because there's a lot of calculations that they're doing behind the scenes. So sometimes you have to kind of give it a minute. This is also a funny thing in data science that is also true, no matter what programming language you're using. The bigger the data set and the more points that you're messing with, then it can take a while. Like I know people in the communities like astronomy, and they might like literally let something run for a day or a month of calculations. So like it can be pretty intense. I don't know the exact values, depends on what kind of field you're in, but like it can be pretty intense. So, you know, many universities often have a supercomputer center specifically for these purposes. Although they're not as relevant today because people have GPUs, and GPUs are monsters. But like, it's kind of a funny accident of the video game industry, because the video games needed so many powerful calculations to make things look realistic. Turns out that's also really useful for science. So.
Yeah, the whole blockchain thing kind of ate up all of those GPUs.
That's true-ish. I mean, that it is true that they've definitely caused a lot of problems, although some of the algorithms that are being used on the blockchain side will hopefully get rid of some of that, like proof by stake and some of that kind of stuff, or proof by storage. And
Yeah, they've been doing a lot better making specific cards, you know, for calculating that more efficiently, which is really nice. But yeah.
Oh, I meant more that some of the newer things like the Ethereum chain is moving to proof by stake, and it'll get rid of a lot of that, because it is, even in the best case scenario, it's super wasteful, right? Like it's just a total waste of power. And like, you know, I mean, obviously people have different opinions on this stuff, but I just mean like it's very power hungry considering what you get, which is a fluctuating currency. I mean, we have currencies other ways too, so, but yeah. Okay, another minute at the most. And if you're ready at this point, feel free to toss in any hypothesis that you've garnered from looking at these into the chat. What matters here? What is influencing the relationship between children and BMI? What has influenced the relationship between children and BMI? Okay. All right, so go ahead and type in your stuff, and I think we're ready to go. So if you have any thoughts, it can get a little tricky. I'll show a couple. I'll show one on the screen that I made. I'll let people type out as we go, though. I do see a few. Oh, age is a factor in the number of children in BMI. Okay. Okay, so let's take a look at a couple of them and kind of just go through, because how do we use this information to try to make decisions about our data set is one of the skills that you teach. So on the screen right now, I have an example of my two are add selected columns, children, BMI, and then my selected factor is smoker. So can someone say in English what scientific question this is trying to answer? Assuming that the data set were real, we're pretending, right? What scientific question would this be trying to answer?
Is smoking a factor in BMI in children? Hopefully children are not smoking, but
yes, that's exactly the type of thing that you're asking. Like we're looking at the relationship between BMI and children. You can imagine there's all sorts of relationships that you might be interested in the correlation, that there might be external factors that are related to. And it could be that smoking is one of them, or it could be that it's not. It could be totally unrelated. In this particular case, with children and BMI, the relationship between children and I, do we think smoking is impacting this relationship or not? To orally describe, on the left-hand side, you do see the relationship go up a smidge for no, and it's maybe down a smidge for yes, but it's pretty small difference in the trend lines. And there's a lot of dispersion, a lot of dispersion. So what do we think? Is this a real relationship or not? Is smoking a factor that we should care about?
Seems negligible.
I hear one seems negligible. Anyone in defense of smoking? Okay. And I think that's the conclusion that you would come to. Now, in practice, when you're doing the statistics for this stuff, there are some things that you have to do to formalize whether or not this can go away in a model. But oftentimes what scientists do is they look at a bunch of these combinations. It's not a fishing expedition, it's just exploratory. And then they try to rule out things that would not be related. And this is one where if you looked at this relationship only from this data set alone, would probably rule it out as not being relevant. Okay, so let's pull up a couple more. And in data science, this is really what you do, and this is why you separate things out. So Tim Lockwood said age is a factor in the number of children in BMI. So I tried this one too, and I actually did it in a slightly different way because I wanted to make the chart different. But so this is the code that I used, and I'll put it up for this particular one. I flipped the result slightly. So I made the factor children because, oh yeah, why? Actually, maybe I should say that. Why would I do that? You can look at the data set and figure that out. Why would I flip children and age as the factor or the selected column? Can anybody figure that out? Oh wait, you know what? If I show it visually, it'll be maybe obvious too, and then I'll orally describe. If I make age the selected factor, if it pulls up, there it is. I have a chart. And in that chart, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rows of charts. 1, 2, 3, 4, 5 columns of charts. And the legend is so small that it just can't. Ironically, a screen reader user could get that information, but a sighted person, no chance, right? The problem is this is like 50-ish charts. And you can't even really tell which one is which when you have this kind of thing. And so why? Why is it that having age as a factor is such a problem?
Because there's a large range.
Yeah, because each individual age is there. So there's two ways I could sort this out. One would be to filter the data. And the second way would be to flip the factors. There's less children, so although it doesn't mean quite the same thing statistically, we're going to flip them. So my selected factor is actually going to be children. Oops, I pressed the wrong button. And my selected column is going to be age. So technically, this is looking at the relationship between BMI and age with children as a factor, but that's okay. Okay. So now we've got a 3x2 grid, or 2x3 grid, depending on how you do it. And in this particular case, we've got 3, 4, 5, 0, 1, and 2 children. For each of the charts, there's quite a bit of dispersion. And you'll notice that once you get up to 4 and 5, how much data do we have? I'm seeing some head shaking.
Not nearly as much.
Yeah,
Not
considerably
nearly
less.
as much. Yeah. So what that means is those results are not going to be very reliable. So and you can get to this with a screen reader as well. If you go to the legend, and you press enter. Do you press enter to go into the legend? Oh, I thought you did.
I think they removed that because the legend reads out when you go into the chart area now.
Oh, that's right. We did change that. It'd still be nice to get into it though. I don't know. We'll figure
There
that
you
out. If you look at the legend, it has regions 0, 1, 2, 3, 4, and 5. Okay. I know I'm taking these charts a little bit slow, but I'm doing that on purpose because they're complicated. Like this is like about as complicated as these charts get. And so it's hard to understand them. 0, 1, 2, 3, 4, and 5, that's the number of children for each spot, gives the color and the value. And if you look at 4 and 5, there's this number there that says R squared. And we're going to talk about this a little bit, but I want to remind you that the letter R in statistics, as bonkers as it is, means correlation. Correlation.
Correlation.
Yes. R squared is the correlation squared. Okay. Now, if you're not a stats guru, does anyone remember why on earth do they square the correlation? There's a really good reason for it, but why is that? Forget the numbers. Why do you do that? Like there's a correlation, and then sometimes in statistics we square it. Why on earth would we do that? Anybody know?
Get rid of negative values?
That's one, gets rid of negative values. Why not just take the absolute value then?
So they want to make our brains hurt.
That's true. Hashtag facts.
Avoid imaginary numbers that way.
There's no imaginary numbers in this stuff, but that's a good guess. Typically, you see imaginary numbers a lot in electrical engineering, digital signal processing and such, but you don't see them as often in statistics, pretty rarely. Actually, I don't know if I've really ever seen them. They're probably in there somewhere. Maybe there's in some calculation somewhere. Maybe eigen stuff. No, I don't think so. Anyway, it doesn't matter. So the reason is because in statistics, we have a concept. It's a concept, and it's called variance accounted for. Okay, variance accounted for. They call it a VAF score. Variance accounted for is used across many kinds of statistical tests that all use different kinds of equations. The details of them don't matter, but variance accounted for is often interpreted, although it's not always completely correct, but it's in the ballpark. Variance accounted for is interpreted as the percent of the variance that is related to this relationship. So what that means is if you have an R squared of 1, that the wobble in the data fully represents the relationship. And if it was a 0, then you're going to see a big mess. Okay. So what that means is the value of 4 here has an R squared of 0.0606, which means about 6% of that wobble is accounted for by this relationship. About 6% of that wobble. So now answer me this. If it's 6% of the variance is accounted for, is that a real relationship?
No.
Other opinions? The answer is you can't tell. And the reason you can't tell is because whether it's a real relationship at a variance accounted for of 6% depends upon how much evidence you have. And when you think about it, that makes sense. If you had a relationship that said it accounts for 6% of the variance and you had 5 data points, is that enough evidence? Just intuitively.
No.
No.
No. What if you had 100 billion data points, but it said it was 6% of the variance?
That's a different situation.
It's a different situation. And this is why if you look at things like, and this is where it's kind of fun for data science, if you look at things like vaccine trials of the FDA, that's why they always start out with these small scale trials and then they slowly build them up because they're like, hey, run the small one, do a phase 1. It's only for safety. We're only checking certain things. And hey, there's a certain number of people. And then the phase 2s get a little bit bigger. And then the phase 3 trials are much larger depending upon context, right? They're kind of like building up that evidence and seeing if we get the same result as we go while trying to minimize harm. They're not perfect or magic, but nonetheless, that's the idea behind them, right? So the other thing I want to point out here, if you look at 5.0, the R squared isn't 0.066%, it's 0.0052 or 0.5%. So what that's telling you is that somehow, if you have 4 children, it explains 6% of the variance. And if you have 5 children, it explains 0.5% of the variance. Does that sound right?
It's sample size.
That's probably an indication that the sample size is too low. When you see just tiny variations in the data having such a large impact on the variance accounted for, it's usually a red flag that you don't have enough data. That's usually what it means. So if I was interpreting this as a data scientist, I'd be like, well, can we find more people with 4 and 5 kids and kind of like hammer this out in a little bit more detail? Because it looks like we don't have enough evidence to draw a firm conclusion about this data. It looks like there's a lot of dispersion in the data. Okay. Is everybody with me? We've got multi-charts. We use them to explore scientific hypotheses, and we usually use them to sort out whether competing ideas or factors with all their levels are related to the hypothesis that we have in question. In other words, we're often trying to rule out alternative explanations. We're basically saying, okay, suppose that the relationship between BMI and children is real, hypothetically. What can get in the way of that relationship? And what do we need to rule out in other studies? It's a scientific way to do that. Let's do one more. Because oftentimes we do this with our data sets quite a lot. And so when we run studies in our lab for real, we often do this across quite a few sets of charts.
So I did BMI and charges as columns and children as the factor.
Yeah, you did what now?
BMI and charges as the columns, and then children as the factor. It's kind of interesting. It looks weird.
Okay.
Maybe you could explain it. I don't know. I don't know what I'm seeing.
What was the selected factor?
Children.
Children. Okay, sure, we can do that one. Let me generate it real quick. Okay.
Initially, I made the mistake of putting charges as the factor. That was cute.
Yeah, but since that's a quantitative variable, you probably had like 150 charts or something, right?
It literally never populated. I let it calculate for like 2-3 minutes, and then I was like, oh yeah, there's a lot of those numbers.
That sounds right. Okay, so this one's interesting. Okay, so I'm going to orally describe again. In this particular case, there is the factors and such are charges, BMI, and children. I'm sorry, charges and BMI for the selected columns, and then selected factors is children. So first of all, we always take a step back and we ask, what's the scientific question that we're asking here? So Mike, you proposed it. So what's the scientific question we would be asking, assuming that this data set were real, right? I don't know if it is, but
yeah, like, is there a relationship between charges and BMI factored by how many children you have?
Well, what does that mean, factored by? What does that mean?
I mean, I don't know. It's just seeing if it's somehow different. I don't see it.
Dude, it's all good. It's basically asking, is there anything that screws up this relationship? And you can imagine how scientists do this all sorts across data sets. How do we know climate change is real? Well, you know what? They do it the same way. They take some data, they measure it compared to temperature, and then they put factors across all sorts of variables that they've thought of to try to figure out, do those factors screw it up? And under what context and under what rules? Same with any kind of scientific question. These scientific questions aren't really special. They're just another example of another question. Right? And so in this particular case, it would be asking, if we have a relationship between BMI and charges, does the number of children impact that relationship? Right? Does it impact that relationship? Different statisticians use different phrases to represent this. And I'm using slightly non-technical language, but I think that that's okay, right? So anyway, okay, so on this chart, I see again, 0 through 5 number of children. And interestingly, when we look at the relationship between BMI and charges, normally what we observe is that the relationship is a significant positive slope for the line. And so as the BMI goes up, you tend to get charged more, basically, is what it comes down to. But what we notice in this chart is what? We see an anomaly. And what is that anomaly?
5 kids.
5 kids. So in the 5 kids chart, what we observe is that as the BMI goes up, and if you have 5 kids, that the charges go down. Why is that? This is very confusing because if you look at the legend sure says that it's valid, right? It says that the BMI is 0.0 times charges plus 3.319, R squared of 0.0474. Boy, that number sure seems big. It explains 4.7% of the variance, but that's clearly wrong. I mean, the number might be correct, but that clearly doesn't represent the situation. Why not?
Because there's like 18 data points there.
There's almost no data. That's number one. And then there's another little thing here that is a little bit hard to figure out. But you see where it says BMI equals 0.0 times charges? That's literally saying that you multiply something close to the number 0 times the charges value in the equation. So that would mean you take
Which gets you 0.
Yeah. Basically, it basically means it's really not very predictive at all, which makes sense because it's not, a very big effect, right? We're still talking effects that are only in like the 3 to 6% range. So even under the best circumstances, this is not a strong relationship. So yeah, really the way that we can explain this particular chart is that, yes, it's true that the 5 children model did actually go down, but we can't really tell if it's spurious, but it's probably spurious, right? So this is one of the challenging things about data science is that sometimes it's pretty tricky. You can't know for sure, but you can hypothesize that if you've only got 18 or whatever it is people here, that's just really not that much evidence. And it's okay to say that in a scientific paper or something like that. So, or even just to presume it. I mean, you just have to be careful to not assume that it's causal. Assuming that it's not is always a little bit more fair because you're not claiming something's real. Just say you don't know, and that's more normal. So, okay, so the conclusion that I would draw if I was looking at this chart, I would draw that the number of children really doesn't have much of an impact across this particular factor. So the number of children as a factor doesn't really impact the relationship between charges and BMI very much, if at all. Does anyone disagree or? Yeah, okay. All right, let's do one last one because that was the one I was going to get to. That's okay. And that is, I want to do region because Louisa had mentioned it. So I'm going to do one last one. And I'm going to put Oh, Sam Shaw has appeared. Welcome, Sam.
Hello.
So for the very last one here, I've got region. And again, I've broken down my values by southeast, southwest, northeast, and northwest. I put children on the x-axis for this one. And then if we look at the legend, all of the R squared values are now less than 1. Less than 1%. And we have to remember that this is not like the traditional regression where we put in this as a factor. They're calculating this to just figure out the trend line. So this doesn't give us the exact value for the regression. It's the regression on each individual subchart, right? But the point is that the calculation seems to show that the amount of difference that it makes is pretty minimal at best. It's not very explanatory. However, and I think this is slightly interesting, if you look at southeast, the trend line does go down a bit. If you look at southwest, it does go up a bit. If you look at northeast, it goes down a bit. And if you look at northwest, it goes up a bit. And so one very common thing that students might do is they might claim, well, but look, I see that some of them are going down and some of them going up. So here's my question. Why are some of them going down and why are some of them going up? Can anyone know?
Well, could be the amount of data you have for that region.
Could be. What else could it be? When data scientists collect data, is the data perfect?
Yes.
Exactly right. There's variation in how data is collected. Maybe the BMI numbers are off a little bit. Maybe, maybe their classification of Southeast versus Southwest is imperfect. Like, how do I play? Florida is Southeast, but is Florida the same as Georgia? I don't really know. I actually have no idea, but that's not really my point. The point is that sometimes we've made classifications and the classifications themselves are imperfect. And as such, we get what is essentially random variance. And when I say random variance, I don't mean it's provably a random variable. What I mean is, at least in this context, is it could just be chance. It could just be measurement error and stuff like that that are getting in the way of the relationship that we're trying to measure. Right? And you actually see this in real data. One of the classic examples, and maybe this is mildly sensitive, but it's the truth, is the whole vaccines and autism debate. If you look at the actual data, there's no relationship. It's random chance. But you still observe things go down or up, right? Because it's not an exactly perfectly zero, because that doesn't exist in real data. So if I recall, remember, it actually goes down a little bit if they're vaccinated, but that's actually not the point. It's fake. It's random chance, right? And so there's a lot of stuff that happens on this in data science. It's never going to be exactly perfectly zero or exactly perfectly flat. And so one of the lessons students have to get is, how do I make sense of something that isn't perfect, that lacks this perfection, this mathematical perfection, while still making sense of finding something that is real? Like, how do I tell the difference between those two? And we'll talk about that, formalizing that intuition a little bit tomorrow in the lesson on regression. But for now, the lesson is, when we separate things out, we can use these factors, and we do that for data exploration. And sometimes we have to make a lot of guesses and assumptions. Okay, I think that's all I wanted to say in terms of multi-charts. Hopefully it gives you a sense of, number one, how you make them, although that's the relatively easy part. But number two, how you interpret them, which I think is quite a bit harder because they're a little complicated. So, any questions, thoughts, concerns? Or you're all bored? Maybe Tim. I'm just kidding, Tim. Okay. All right. Well, then let's walk away from our computers for 10 minutes. And after we do that, oh, and I'll stop the recording.